Okay, welcome to topic 7. In this topic, we'll be doing static and dynamic force analysis. Now, the reading assignments are here from the book. Again, they're just recommended. You might say, well, hey, we've already done static and dynamic force analysis. That was the power equation stuff. And you're right, in power equation, you were able to analyze systems using energy and power arguments so that you could calculate what the external forces or moments, or just loads really of any kind, are imparted on the mechanism. You were able to learn all the tools to deduce that. And it didn't matter if it was static or dynamic, if it was stationary or moving or accelerating or you know, for any scenario, the power equations worked. Okay, but you might recall, well, let me just read this. Forces that do not do work on the system as a whole, such as pin forces and contact forces at smooth surfaces, and joints really, do not appear in the work term. So remember, you know, the forces, if you have two links and they're kind of pinned together so that they can rotate, one link puts a force on the other and that link puts a force on it. And those internal forces, or the internal forces within the beam, if you take a cross-section and measure the forces from stress, those never show up anywhere in the power equations or in any work terms. And so you can't calculate those. You can only calculate external forces. Okay, so in this lecture, I'm going to give you new tools, different tools, both mathematical and graphical tools that will help you analyze an entire mechanism so that you can not only solve the external forces using this different approach, but also solve, for the internal forces. Okay, and we're going to start out by showing you all the ways to do this for static situations, and then the final topic will be how to do the same thing for dynamic situations if the thing is moving or accelerating or doing something interesting. Okay, so let's do some background, some simple background and notation. Okay, this is deceptively simple, but these principles are very important to understand. Okay, so first of all, the forces that link I exerts onto link J will be denoted in this class as Fij. Okay, so in this case, say you've got two bodies and they're acting on each other. And of course, according to Newton's third law, for every action there's an equal and opposite reaction. So if one body hits one body, whatever force that body hit it with, that body hits it back with the same force in the equal but opposite direction, right? With equal magnitudes, opposite direction. And so the convention we're saying here is that if the force, and notice it's a vector with a line below it, if that force is Ij, that means that's the force that I exerts on J. Now, if you wanted to do the equal and opposite force, it would be Fji, because it's the force that J exerts on I, right? So what I'm saying is the order of those two subscripts matter for the convention that's going to be used in this topic. Okay? So notice Fij equals the negative of Fji, because they're equal and opposite forces. The equal is the same magnitude, the opposite comes from the negative sign. And notice the force I imparts on J, and this is the force that J imparts on I, which is why the order. Okay? So let's look at common scenarios. Say you have a link J and a link I, and they're pinned together with a smooth pin, okay, which means friction-free. If there's no friction, if it's just friction-free, then these bodies cannot impart anything more than a force on each other. So they can't impart moments. There's no way to impart moments on them. And whatever the force is in whatever direction magnitude, they will be equal and opposite. So this is, you can see it broken apart. This is from link I over there on J, and this is from link J on I. And you can see how they're labeled, the subscript. Okay? So now say we have two links in smooth sliding contact. Okay, so two links that are just contacting each other And if it's smooth, that means there's no friction, which means the force that this one imparts on that one and this one imparts on that one have to both be normal to where they touch and at where they touch. And this point is just a single point, right? And so this is in the normal direction, perpendicular to the line tangent to it, okay? And so you can see that. But now if the exact same joint was allowed to have friction, well, then there would be a normal component and a frictional component that is tangent, just like you can see here. And they would, of course, be equal and opposite by the same fashion. Okay? So that's important. We'll evoke these simple concepts later in this lecture, but it's important to note if you just have two bodies touching, they can't impart a moment on each other. Okay? They just impart forces, and if there's no friction, those have to be normal. If there is friction, they can point really in any direction when they're summed together. Okay? Okay. All right, so that's let's do a little bit about the analytical method. So there's an analytical way that you can take these forces into account. Okay, so this is still hopefully a review for most of you. So anytime you have a body or a link, okay, you can take it out of the mechanism and just kind of draw a free body diagram on it, where you show all the forces acting on the body, and it's great if you know where those forces are acting on the body, of course, and then all the moments or couples or pure torques acting on the body, okay? And then when you have those drawn for each link, you can do you can sum those forces and sum the moments, and if they all equal 0, then that means it's in static equilibrium. Okay, so if you have a mechanism, there's a bunch of things loading it, but it's not moving, and it's not just at rest for one instant, but it is literally static over time, and nothing is moving, there's no velocities or accelerations, then of course the forces and the moments better equal 0. Okay, and why is that? Well, because remember F equals ma, and if the force equals 0, then that means the acceleration is 0, and it's at rest or moving at a constant velocity, which is essentially at rest so far as frames of reference are concerned. Okay, and same thing with moments. Okay, so a couple things to know in a two-dimensional setting, like this whole class is kind of for two-dimensional scenarios. You're going to have all your forces that are acting on the body will be in the plane with two components, okay, an x and a y component pointing in the normal I and j, the unit vector I and j, where I points in the x direction, j points in the y direction, right? And all the moments will be coming out of the page at you, or either coming out or into the page, but nothing in the plane. Okay, so right, so there's pure moments, and then there's moments that are created by the forces acting on the body. Okay, now interestingly, if you're doing this top equation, you're summing the forces, setting them equal to 0. You don't really need to know where the forces are applied, and there's no knowledge about that in the vector of the force. Remember, force vectors are only they only tell you the magnitude and direction. They don't say the location where they're acting. Although that information is important, but those vectors don't contain that information. So if you had a bunch of forces acting on some potato here, and they had their lengths according to their magnitudes and their directions established, you could think about all their points where they're loading it changing. You could shuffle them around any way you want, because those forces have no knowledge about their location embedded in the math. And all you do is you sum their x components and have them equal 0, and you sum all their y components and have them equal 0. And notice those equations, when you do that, are independent of where the force is being applied. Okay. Now, when you sum the moments, though, it's the same story for pure moments or couples. If you have pure moments or couples acting on the body, those also just have a magnitude and direction. You know the direction's perpendicular to the plane, and the magnitude is whatever the magnitude is. It's the length of the vector coming out of the plane, right? But they don't have locations. So if you draw a circular arrow on a body saying it's a pure moment, it doesn't really matter where you draw it. It's just you're just going to sum them all together and set them equal to 0. But if there's forces involved, to find the moment caused by that force, you definitely need to know where the force is being applied. Okay, so for instance, say you have this force F, and it's acting at A. That's a subscript, so F is acting at A. And you want to take the moment about point O. In other words, find what the moment would be caused from that force about point O. Well, then what you would do is you would take a vector that points, a displacement, or a location vector that points from O to A in units of meters, in distance, right? And you would cross product it with F, which is in units of newtons, right? And here that we've already in this lecture switched up the conventions. You have to be able to switch conventions and understand, what they're doing for different scenarios. The book has different conventions. Right now we're saying, the book would have been R just AO, saying it's pointing from O to A. Here in this lecture we have A/O, and you might think, well, according to the book, that's A relative or with respect to O, as if it's some apparent thing from the past lectures. That's not the case here. We're saying A/O means it points from O to A. Okay, and so we take that vector and we cross it with that, and hopefully you know how to do cross product math. You take this times that, and then subtract it from this times that. And you get this, and it's in the k direction. Okay? So if you had a bunch of forces and some pure moments acting on it, you would pick the point where you want to take the moment about, and you would define all the vectors that point from that point to where the forces are being applied. You would cross product them all, and then you would add those all together and also add them with the pure moments. And all those moments summed together must equal 0 if it's not going to be rotating, okay? If it's going to be static, okay? And then, of course, the forces have to, the different force components have to all add up to be 0 as well, okay? Okay, so a couple insights. This one doesn't care about location. This one does if there's forces causing moments, and you know how to add them all up and set them equal to 0 if it's a static scenario. Okay, the question is, well, where do you pick the point? Like, how did we know to pick this point? Say we had a bunch of forces on it. How did you know to pick this point to then draw this vector to cross product with this and sum all the moments together? Wouldn't it be different if we picked a different point, the moments caused by all the forces? And yes, unless they're in static equilibrium. And I'll prove that to you, okay? So imagine, the potato's not here, the body's not drawn here, but say here's some forces F1, F2, and F3, and say they're acting at these 3 points on some body, okay? And you want to find what is the moment about this point O caused by these forces. Well, you take that vector R1 and cross it F1, and then you add it to R2 cross F2, and you do this, okay? So you do that for all 3. And that would be the moment about point O, okay? And then you think, well, let's try and take the moment about a different point, say point P. Well, if we try to take the moment of, about point P as a result of these 3 forces on a body, you would take a vector that points from there to there and cross it with F1, vector that points from there to there and cross it with F2, and there to cross with F3. Well, let's use, though, the vectors we already know, but define a new vector, A, that points from here to here, instead of doing what I just said, and say R1 plus A will be that vector that points from P to there, and you cross that to F1. And you go through and do the same thing with all of them. Okay, so you can see how if you add A plus their location vectors, you would get the location vector that points from P to where the forces are applied, and then you cross those. Okay, and that would correctly be the moment at point P. Okay, let's distribute these forces. So if you distribute all these things, Okay, you put these in all there. And of course, if you take R1 cross F1 and R2 cross F2, it's this. So we simplify that into MO. And the only thing that's left is this. Okay, which now if we pull the A out, we get something like this. Okay, so surely, MO is different than MP, and here's how they're different. It shows it's MO plus all this stuff. Okay, so yes, if you have a bunch of forces on a body, and you take, it very much matters what point you take the moment about. There'll be different answers, unless they're in static equilibrium, which this equation shows. If they're in static equilibrium, or if say it's rotating, so it's not static, but as long as just the forces all sum to 0, then this goes away and MO equals MP. Okay, so if something is in static equilibrium, meaning all the forces and moments sum to 0, then it doesn't matter where you take the moment about, whether it's O or P. These moments, this will always be 0, and MO will always equal MP, and MO and MP will be 0 if it's in static equilibrium, right? But say there's a scenario where the forces all sum to 0, but the moments don't sum to 0, then we've also proven that we can take the moment about any point. It doesn't matter because these will still cancel to 0, and MO will always equal MP. They'll be the same no matter where you pick the point, okay, if the forces all sum to 0. Okay, but so far as static equilibrium is concerned, you can pick a point anywhere you want, sum the moments, and they will always, you always set them equal to 0. And it doesn't matter. Okay, and that's what this says. Okay, so let's do the first analytical method, and it's basically a free body diagram method that I'm sure you've done free body diagrams in either high school or freshman year here. They're one of the most important things in physics, right? Mechanics. And so, but maybe you haven't done it for a mechanism. Okay, so here's how you apply this for a mechanism. The question is, say you have a 4-bar, okay, and you want to find out, well, first of all, here the mechanism moves in a vertical plane. Gravity acts in the negative y direction. So there is gravity pulling down in this direction. So the whole mechanism kind of would want to collapse on itself if it could move. Okay, and we wish to find the moment M2 that acts on link 2 and makes the 4-bar static when a moment M4 is applied to link 4. So basically for this example, we give it an M4, so M4, it's some moment we're imparting on there, and then it's heavy, it's got gravity, it's pulling down, and we want to find out what moment M2, we don't know the direction, well, we would know the direction, it would be in the opposite direction, right, to hold that up to be static. But always draw it in the right as positive, and the sign conventions will take care of themselves. But anyway, the question is, what is the M2? What is the value of that moment that will hold up the weight of the mechanism and resist M4 so that the mechanism is static. It doesn't move. You take pictures of it over time and it's in the exact same position. Okay, so how would we solve that? Okay, well, we did that basically in the last lecture using the power equation. But let's do it here with the free body diagram analytical approach, okay? So you take each link out. You don't need to do it for the ground because, it's not moving at all. But let's take it out for link 2. Okay, so let's draw a bigger picture of link 2. And let's look at this here. So you ask yourself, what are all the forces and loads and moments that are acting on this? Well, M2 is acting on it just from up there. Okay, gravity is acting on it, which means it's M2, the mass times G, and you draw it down because that's down. Okay, and is there another moment acting from the ground on link 2? Well, no, it's a pin joint, and by the way, you also assume they're smooth unless you're told there's friction in there, and so there is no moment that can be imparted on that, just forces, and there could be a force in any direction, but we're going to break it into the components. And we're going to draw them always positive, and if we stick to that convention, we'll calculate, if it actually ended up being negative, it'll give us a negative sign. Okay, so just always, if you don't know the direction of the loads, or even if you do, you can draw them positive and it'll work out. Now gravity, of course, is down. Okay, so we're always going to draw these at the pin joints positive, and make sure you label them correctly. So this is F12x because this is the force that 1 imparts on 2. And this is the force that 1 imparts on 2 going up in the y direction. And same thing at this pin. These are the forces that 3 impart on 2. So it goes F32x, F32y. Okay? And those are all the loads that are on that link. Okay? I think you could argue there's no other loads on that link. And so now we can apply those, we can sum the forces and set them equal to 0, and sum the moments and set them equal to 0. So first equation will be sum the x components of force. Okay, F12x, this one, plus F32x, this one, equals 0. Okay, great. Second equation is do the same thing in the y direction. Okay, we drew this positive, so keep it there. Okay, but minus m2g, because we drew it down, plus F32y, all the things in the y direction, set them equal to 0. Okay, now we're going to sum all the moments together. And we could pick any point we want, of course, because when things are in static equilibrium, not only are the moments the same no matter where you pick the point, but those moments are 0. Okay, so you could pick some random point out here, but you might as well pick a point that makes your life easy and simplifies the math. So if you pick one of the pin joints, or at least the center, you'll see you don't need to. These forces don't exert a moment if you take it at that point 0, because there's no moment arm. Okay, and so let's do it about O, as it says here. But that's just arbitrary. We could have done it about A. Okay, and if you do that, you get this equation. This is the third equation. Okay, where you basically take 1/2 of R, so it's a vector that points from there to there. Okay, and you cross product it with this one. Okay, that'll be the moment in this direction from this force. And of course, these forces don't exert a moment about 0.0. And then you'd add it to R2 cross the force up here, which in this case we're just combining it to solid F32. Okay, and that's that. And then we have to add it to this just moment, this pure couple M2, which we could have drawn anywhere because it doesn't have a location. This is not saying it's about this point. You could do it anywhere. Add it all together, and it equals 0. Now, if you break this up into the different components, you get something like this. Okay, so notice this one is just that distance times this value, and that's negative because it's in that direction. Okay, this one is basically just this distance times that one, and that's positive. Okay, because it's going that direction, and this one is this map, that distance times that, that's negative, it's in that direction, then this is positive, how we've drawn it. Even though we don't know if it's positive, it'll come out in the math. Set it equal to 0. Okay, so now there's no vectors in there. Okay, so very good. Now we have 3 equations from this link. Okay, which you'll from any link you pull out of a mechanism that's a planar mechanism, then you're always going to have 3 equations. Okay, and of course, if it was a 3-dimensional mechanism, for every link you pull out, you'd have 6 equations: the sum of all the forces in x, y, and z, and then the sum of all the moments about x, y, and z. Right? Okay, but in this case, we just have 3. All right. Okay, but that's not enough to solve the unknowns. We don't know what M2 is. We don't know what these two are. And we don't know what those two are. So the only thing we know is M2G. So we don't, that's a lot of things we don't know, and we only have 3 equations. So let's do the free body diagram on another link. Let's do link 3. Okay, link 3. You could draw like this, and again, there's no moment acting on link 3. There's just gravity, M3G, acting at the center of mass. At point G3, right? And then, again, these can't impart moments. They only impart force. We don't know what direction is, so we'll break it up into 2 components. And notice how we label it. It's F23x. That means from 2 on 3. And then this is from 4 on 3 for those 2. And we draw them in the positive direction. Okay, then we sum the forces in the x, we sum the forces in the y, and again, because it's in static equilibrium, we can pick the moment about any point. Let's just say about A to make our life easy. The other equally easy one is to make it about B. We could also make it about the center, anywhere we want. And now we do similar thing. You can see 1/2 R3 cross the gravity. That's the moment from this one. These ones have 0 moment because we're doing about A. And then we're going to do R3 cross this force, and that equals 0. Because you set them all equal 0 because it's static equilibrium. Okay? And then you can simplify this into this. And I'll have you look at that at home, make sure the signs are right, and everything is good. Okay? Okay, so we just got 3 more equations. Okay, now finally, I'll bet you can guess. We're going to do the same thing on link 4. So zoom in on that and add all the loads you know. This is M4G pulling down. And this is the force on this pin caused from 3 on 4. This is why it's F3-4. And this is from the ground on to 4, which is F1-4 in the x and the y component. Okay, and then of course, you have to add the moment 4, and again, you could have drawn it anywhere. It looks like it's rotating on this point, but you can put the moment anywhere. And but that pure moment is on it, and that's one of the things we know. It was apparently given to us in the question. It said we know M4, find M2. Okay, so again, sum the forces in the x component. There they are. Okay, sum the forces in the y component. There they are. And then again, pick any point you want to simplify your life. Probably pick about C, that's fine. And then sum the forces, okay? Now, okay, so you get 1/2 R4, points from there, cross to this. We have a negative sign because it's going down. And then R4 cross to this. And then you add M4, notice the K here, because we know it's coming out of the board. Set that equals 0. Now you can simplify this down into these components. This might look confusing because if you go through here, you say, okay, so 1/2 R4 is right there, and times mg, that should be a positive moment, but it looks like it's negative here. Well, the reason this is negative is because R4x, as it says here, is already negative by how it's drawn. Notice the arrowhead, the tail goes from here and the arrowhead is up there, so the component is already negative. So when you plug in that component, it'll make that positive, okay? And same thing here, R4x times F34y is basically that distance times that F34y. That should be negative, but it shows positive here, but that's because this is a negative number. And when you plug that in, because this is negative value in the negative direction, that'll be positive. So now this is right, and so everything's right. Stick to the sign convention, and you'll be good. Okay? Okay, so great. So we just got 9 equations that we know are true as long as this is in static equilibrium. Well, the question is how many unknowns? Well, right. Well, we don't know these forces, so that's 1, 2 unknowns, and we don't know those forces, that's 1, 2. These ones we do know. So basically for each of the links we looked at, all 3 of those links, link 2, link 3, link 4, we don't know the forces at those links. Two there, and then at A there's 2 there on 2 and 2 on 3. So it'd be 2, 4, 6, 8, 10, 12. Okay? So we don't know those 12 forces at all, the edges of the links. And we also don't know M2. Okay? So there's really 13 unknowns. Okay? And we only have 9 equations. Well, but you might say, we're missing some equations there. And you're right, because those forces at point A and B are equal and opposite. So F32x is equal to negative F23x, because the force imparted from 3 on 2 is equal to the negative of the force imparted from 2 on 3 in the x component. So these are 1, 2, 3, 4 new equations. So 9 equations plus 4, that's 13. So fantastic. So with the 9 equations we did from static equilibrium and these extra 4 equations, we now